It's difficult to comprehend how much life has changed for our species between 1900 and 2000. The photograph on the left is from 1903, the photograph on the right is from 1969. Chariots were invented around 2000 BC and were the fastest form of transportation known to man for around 3,800 years, until trains in the 1800s. 100 years later, we were flying. 20 years after the Wright brothers started their experiments, air travel had become routine. 66 years after the Wright brothers, we were on the moon. Hence the quote from Ray Kurzweil at the bottom. Because of the exponential nature of progress in information-based technologies, performance often shifts quickly from pathetic to daunting. The main ideas from this lecture are taken from this book, The Second Machine Age by Eric Brynjolfsson and Andrew McAfee. It is a book that is often quoted in all the tech literature. What it talks about is the many outstanding features of the second machine age, which they refer to are exponential improvement, digitised information and recombinant innovation. This lecture is about those three aspects. This presentation is mainly about GPT's general purpose technologies, and these are defined as deep new ideas or techniques that have the potential for important impacts on many sectors of the economy. Now, Brynjolfsson's second machine age is mainly talking about ICT, information communications technology. It's from, as you can see, from 2014, which is a little bit before when we started talking more about artificial intelligence as we are now. So it is technology of a general nature that can be applied to lots of different situations. Now, of course, when we talk about artificial intelligence, we're talking about artificial general intelligence. So we borrow the ideas of the general purpose technologies because we then apply them to artificial general intelligence, because it's at that point where the agent will be able to provide answers to a large amount of problems in exactly the same way that steam power created lots of different power in lots of different contexts. So we borrow the ideas of GPTs and apply them to artificial general intelligence, which is the purpose of this lecture. General purpose technologies then are technologies, in the word of Brynjolfsson and McAfee, technologies that really matter, the ones that interrupt and accelerate the normal march of economic progress, which is exactly the same as what we're talking about with artificial intelligence. Previous examples on which economists can agree on are the steam engine, electricity comes second, and ICT, information communications technology, comes in third. Other considerations were the building of the railroad infrastructure and also the internal combustion engine, but those three are the ones that come out the top. What you need to do is think about it, and the way I classify them is in terms of digital, exponential and combinational technologies. So that's that tripartite of digital, exponential and combinational technologies is what characterises general purpose technologies, or GPTs. What we have considered on this course is a slide we've seen before where artificial intelligence won the game of Jeopardy. However, you'll have seen this slide before, when it won Jeopardy, that's all it was capable of doing. The emphasis over the past 3 weeks has been around the gains in artificial intelligence have relied less on learning than on superior memory and computation of the computer itself. That's where the success has come. It's not that the computer is able to learn like a human being and retain information the same. So we're talking about two entirely different things. This is an explanation of where the superior memory and computation came from. So the previous lecture was around digital and digitisation, and we considered how the impact of digital has had on the industries of film, music, television and radio. These are all examples of creative destruction. The technology that was created destroyed previous business models that had been existed before. So that's digital. We're on to the next one, which is exponential improvement. On the top left hand side is the first computer I ever used, which was the Research Machines 380Z, which obviously no longer exists. This is going back quite a considerable time, and it's one that I used when I was at school, bearing in mind that there were no computers when I was at school, and this is the first one that it ever bought. The memory contained within this particular computer was 8K, and they decided that they're going to upgrade the memory to 56K. And we thought, how ridiculous. How on earth are you going to use all that memory? That's just extravagant. How things have changed. On the right hand side is the first computer that I used professionally, which was the Apple II. The Apple I was a kit. This was the first major success for Apple, and that was 64K. The one below it is the first PC compatible I ever used, which is a Ferranti 86, which gives you an idea from what year it comes from. And you can see it has 2 floppy disks, as indeed the Apple II has, and that had 128K. It was later replaced with a 20 megabyte hard drive. So if you can imagine, those are what we were working with when I began my career. So we're back to Ray Kurzweil then, who said our brains are not well equipped to understand sustained exponential growth, which was what the quiz was all about that we had during the lecture. So we have linear growth on the left hand side, and we have exponential growth on the right hand side of those two graphs. As I will demonstrate, Ray Kurzweil's great insight is that while the numbers do get large in the first half of the chessboard, we still have to come across them in the real world. To add to this, and as was demonstrated during the quiz that we had in class, again, then we have Al Bartlett, who was saying that the greatest shortcoming of the human race is our inability to understand the exponential function. So, for example, a 10% growth means that something will double in size every 7 years, and just a 3% growth rate means that something will double in size every 23 years. So, examples of these. You often hear companies talk about double-digit growth. If they do that, they will double in size within a mere 7 years. And the one at the bottom is why we should all avoid credit cards for financing long-term debt. A 3% growth per month works out horrendous amount of debt that one can endure over a number of years. So my question is, how many ancestors did we have in the last 400 years? I'll leave you to dwell on that for just 1 second, and then I'll give you the answer. And here we have the answer. The answer is 4,094 over the past 400 years. And you can see that we would have 2 parents, 4 grandparents, 8 grandparents, 16 second great grandparents, 32 third great grandparents, and it gets a little bit unwieldy. So we go to the 4th, 5th, 6th, 7th, 8th, 9th and 10th generation to get to our 4,094 ancestors. You could imagine that family get-togethers, if we lived that long, would be extremely packed. And here's where we get on to some of the exponential functions and an explanation of it. On the left hand side you will see that there is a set of numbers which is 2 to the power 2, 2 to the power 3, 2 to the power 4, so on and so forth. And you can see how by the time it gets to the bottom it's gone within a very short space of time to a very large amount of numbers. So if you imagine this as a chessboard, which is what the Ray Kurzweil statement was a little bit earlier on. And if you think about it like this, you may have heard the old story about the merchant who came along and solved a problem for an ancient emperor, an ancient king or whatever, and the ancient king or emperor or whatever said, "How would you like pay?" He said, "I would like a grain of rice, your majesty." "Oh, that seems very fair," said the emperor, "but that doesn't seem enough. But what I would like is that for every day I want you to double it." So on top left hand side then we have day 1, 1 grain of rice, 2 grain of rice, 4 grain of rice, 8 grain of rice, 16, and so on and so forth. So that seems still quite a good deal because the emperor is thinking in a linear fashion. However, by the time it gets to 30 double-ins, it's at 1 billion. And by the time it gets to 40 doublings, it's 1 trillion. Now, when you consider that 50,000 grains of rice in 1 kilogram, that means a merchant would end up with an awful lot of rice. And you can see this on the right hand side there, where you've got the break, where 2 to the power 40 is the equivalent of a trillion. Now, a chessboard has 64 pieces on it, 64 squares should I say. So by the time you've got to the 64 squares, you've got what's known as the chess number, which is, here we go, 18 quintillion, 446 quadrillion, 744 trillion, which is a very big number. So when you have something that is doubling every year, then it's going to be very large within a very short space, a relatively short space of time, especially as Ray Kurzweil was talking when we get into the second half of the chessboard, which is where we are now. So this is what Moore's law is all about, and there we have a picture of Moore on the top right there with the pipe in his mouth. Looks very majestic. And he came up with Moore's law, which basically said that improvement or speed doubles every year. And I've put that little bit below his picture just to say sometimes we have cheated at Moore's law. This is ways in which rather than we get improvements from the wafer, we've used a number of different layers instead to get this. But this Moore's law, so-called, has held fairly true throughout. Speed, performance have all doubled, while cost has also halved. Now, if you remember, we talked previously about the way in which we have an increase in bounty. So on the digital transformation slide, we talked about bounty's increase in volume, variety and quality, and the decrease in cost. So this is an example of the bounty that has been provided by digital technology. The change in the use of the silicon wafer to the ways in which it is being layered as what is known as brilliant tinkering that has enabled us to get these increasing performance and speed from the silicon chips. And as a result of that, the Apple iPhone 5, those of us that can remember that, was the equivalent performance in 1985, which was around about the same time I was playing with Frantic Computers, with a Cray 2, what was then a supercomputer. This means that everyone has the equivalent of a supercomputer in their pockets. And again, in terms of performance then, a typical smartphone delivers more processing power than the $150,000 Apollo guidance computer that sent astronauts to the moon. The difference then between exponential and linear improvement is that linear is expanded by repeatedly adding a constant, whereas exponential is expanded by repeatedly multiplying by a constant. And you can see the difference between the linear response on the bottom and the exponential response, and you can see the knee of the curve where things start to change most rapidly, that's marked on the graph in front of you. Let's just remind ourselves that the advances that were brought about by playing Jeopardy then were brought about through increases in memory and computational power. And here we see these examples of the computational power. Going from left to right, we start off with what are known as flip-flops, which are a single element device. They are either on or off, they're effectively a switch, and that has increased by core memory, big drives. We've got floppy drives, hard drives, SIMMs, DIMMs, and so on and so forth. And the point is, you can see that how many bytes of memory can you buy for $1, and that has increased over the past 60 years. So hard drives have become 100 million times cheaper. Memory has become a whopping 10 trillion times cheaper. That's a discount of, wait for it, 99.999999999% discount. That could buy all the real estate in New York for about 10 cents if the equivalent performance had been applied to real estate, or all the gold that's ever been mined for around $1. These are the improvements that have been brought about that have generated these improvements in artificial intelligence. Again, just to stress, it's around memory and performance. Now, you may remember when we were talking about digitization that I was talking to you about substrates. Now, substrate is usually applied to silicon, to be fair, rather than the whole of the different types of memory. And this shows the advances in memory from electromechanical, which is a punch card, which was the first version. And we had people who spent their day punching cards with instructions for a computer. Then we went on to the relay. Then we went on to the vacuum tube. There were still examples of vacuum tubes. They tend to be used in audio these days for very highly specialized audio. Audiophiles prefer vacuum tubes. Then onto the transistor, and ultimately into integrated circuit. So you can also see the increase here, and just to reiterate that the scale on the left hand side is a log linear. So that's not just a linear improvement, it looks linear because the exponential has been effectively compressed. And you can see, for example, 10 to the 12, 10 to the 13 at the top left hand side. So cutting the cost of computers a whopping million, which is 10 to the 18 times since my grandmothers were born. Here we see lots of graphs showing the same thing. It's just the, rather than specifics, it's the general trends I want to show you. So we have dynamic RAM in terms of the smallest, and you can see again that's been an exponential improvement. The scale on the left hand side is log linear, and the average price of the transistor has gone again exponentially decreased. Then dynamic RAM price, which is bits per dollar at production, has increased an exponential, as has total bits shipped. These are all graphs from Ray Kurzweil's book, The Singularity is Near. Likewise, you will notice that microprocessor clock speeds have also increased exponentially. On the top right, microprocessor cost, which is a per transistor cycle, has also decreased exponential. Transistors per microprocessor have, surprise, surprise, increased exponentially, as has processor performance, which has also increased exponentially over time. And these are some of the stats that Ray Kurzweil provides in The Singularity is Near in terms of the doubling, or obviously if you're going the other way, of halving times for dynamic RAM, average transistor price, microprocessor cost per transistor cycle, and so on and so forth, all the way down. What we're doing is establish the principles of exponential improvement within a relatively short space of time, which is also due to increase as well. To reiterate the point then, this is all about exponential improvement, and because this has been doubling every year, we're now in the second half of the chessboard. All of this has appeared since 2006, as have countless other marvels that seem quite different from what came before. So what's actually happening now is, and I want you to remember this really important word, it's recursive improvement. Recursive means something that calls itself. It's something that you'll find in programming. It can be a function that calls itself, for example. But it's what, as you see on the right-hand side, is an example of a positive feedback loop. Feedback loops can either be positive feedback loops can either be virtuous or vicious. When we are in a virtuous cycle or a vicious cycle, on the right hand side we've seen what is known as a virtuous cycle, and that's where sales increase satisfied customers, increase positive word of mouth, and you can see it going round and round and round, and there is nothing that one could do to kind of balance this out, which is the whole point of a positive feedback loop. So as examples of persistent doubling, then each step creates the next step. And there is something really subtle going on here, because the improvement is recursive. So each doubling of the performance feeds into the next stage. So as Max Tegmark talks about, this is how technology progresses. Once technology gets twice as powerful, it can often be used to design and build technology that's twice as powerful in turn, triggering repeating capability, doubling in the spirit of Moore's law. So there's 2 points here. First of all, this is how we've got to the point where we're at, where it's about increasing memory and increasing the computational speed, but also for artificial intelligence in the future. If we get into a situation where the human is no longer in the loop and controlling the artificial intelligence, and let's say that artificial intelligence was able to improve itself, you would also get exponential improvement, because it would be recursive improvement, because it would be a positive feedback loop as well. So going much further into the future of artificial intelligence, these are some things that we need to watch out for, that once it gets to improve, then it will start to improve exponentially in a relatively short space of time. Now, if we remember technology adoption as well, technology adoption, it would be no good if this technology wasn't being adopted. It has to be adopted for it to be any good. And just to remind ourselves that the difference between the technology adoption of the humble landline compared to the cell phone has increased within a short space of time. And here you can see the knee of the curve of exponential improvement as we've gone through the invention of the telephone, the radio, the television, the mobile phone and PC. And just at that point, you can see the knee of exponential improvement appearing. So this is when around that technology progress is currently doubling every decade, and implications are technological progress in the 21st century will be equivalent, linear view, to 200 centuries of progress at the rate of progress in the year 2000. So this exponential improvement in technology is due to continue. And we can see this within artificial intelligence, as shown from this graph from The Economist, where we have the Moore's law on the left hand side, where it says 2-year doubling Moore's law, and you can see it's quite a linear growth, and then all of a sudden you get this kick up at the knee of the exponential improvement, and you can see also that AlphaGo and AlphaGo Zero is part of that development as well, which is why we looked at those particular applications within the AlphaGo film. And so the final area, so we've talked about digital, we've talked about exponential, we're now going to talk about combinational innovation, which is also, by the way, known as convergence. And the greatest convergence that we have seen thus far is, waits for the answer, is the internet, because the internet has brought all these things together. So we can now get radio on our internet, we can get films, we can get television. You can see how everything that we were talking about in the previous lecture on digitisation is being digitised, being transmitted, and it's being consumed online. So now we can see where this bounty of exponential improvement is coming from. And what you need to do is to be able to look at what technologies are converging or are likely to converge in the future. So, as our favourite authors, Brindofferson and McAfee, talk about, another school of thought is that it's not necessarily about coming up with something that is big and new, but instead recombining things that already exist. The idea of recombinant innovation, because possibilities do not merely add up, they multiply. So the effect is not linear, again, it's geometric. So three novelties, for example, electricity, the internal combustion engine, and indoor plumbing with running water, all of which came on the scene between 1870 and 1900, were the combinational innovations that, for example, created central heating. And we've also used the washing machine as combinational innovation, which was again running water, and it was also around the electric motor, the abundance of electricity, which gave our wash day back. But I thought I'd add this slide in, which has got obviously two components, and really the theme is that how reliant we have become on our technologies. And mental arithmetic was something that was taught in schools quite a while ago, and now of course we have calculators, which we do actually carry with us everywhere, and how technology has become an integral part of safety systems. And that's part of the AI safety message, is that if we embed them in things like electrical power grid, then if something fails, it can fail catastrophically. Combinational innovation is best shown by the invention, in inverted commas, of the video cassette recorder. Now I say in commas, inverted commas, because actually it's from years and years of development. So the press have this idea that there are breakthroughs, and we find exactly the same with artificial intelligence. There aren't breakthroughs, there are things that are significant that happen, but they are a result of constant improvement in knowledge. It's just that they combine in a particular way at a particular time with something that is newsworthy. The best example of which is we've seen in artificial intelligence is AlphaGo. So the Vizio cassette recorder combined control theory, magnetic and recording materials, magnetic theory with magnetic recording, which is different things, electronics, and finally frequency modulation. And we can see this on this particular chart. It's quite difficult to see all of the detail. That's because there's so much to it. And you can see that the provenance of this technology convergence of the video cassette recorder goes all the way back to 1880 with magnetic and recording materials. In this particular instance, it's hard iron silicon accidentally produced. So an example of an innovation. On the left hand side you can see the various aspects of, for example, control theory, which is something that we'll be covering, around feedback theory, about control theory, about applications to servo mechanisms, so on and so forth, which is then converges with magnetic and recording materials, And magnetic theory you can see converging in two different areas. Then we have magnetic recording. On the right hand side we have electronics, which also coincidentally converges with frequency modulation. And you can see that they all come together at a particular time to be able to produce a video tape recorder with the functions at the bottom of time zone planning, storage, program planning and instant replay. So in essence then, the 1970s video cassette recorder was an overnight success that took 110 years to plan. So we've already considered the idea that Hollywood was scared to death of the idea of the video cassette recorder because it was an example of creative destruction. They could see on the horizon the revenue model that they have been using to press, which was based on income from movie theatres or cinemas. And actually they found that embracing this technology in this particular instance, they actually turned out to be much better off as a result. So what we find with GPTs of ICT, general purpose technologies of information communications technologies, apologies for those 2 3-letter acronyms, is that we can mix and remix ideas, both old and recent, in ways that we never could before, hence the innovation. And a relatively trivial example of the ways in which we can combine these technologies is Waze. And Waze is a GPS system. It's a recombination of location sensors, data transmissions device that's on the phone, and also social networking. So the innovation of Waze is that they put them together in a new way. So here we can see just a relatively straightforward, simple application, but nevertheless an idea of recombinant innovation which then creates value. But of course, it's not just about apps. This is happening now on an industry-wide scale. So this is what we refer to now as Industry 4.0. So rather than just small elements to come together, for example, the way that the app's generated onto the iPhone, this is happening now on an industry level. This is why we refer to it as Industry 4.0, which is when big data, cloud computer, cyber physical systems, automatic robots and augmented realities converge all at the same time. So it's what the steam engine and its descendants did for muscle power. We are now doing the same at the industry level. The recommended reading in this area, it's quite a light read, so when you've graduated perhaps you will consider it, is The Fourth Industrial Revolution by Klaus Schwab. Klaus Schwab is the convener and executive chairman of the World Economic Forum that takes place every year in Switzerland. And that ultimately is what Industry 4.0 is around. These elements of autonomous robots, big data, augmented reality, additive manufacturing, cloud computing, which you have to have cybersecurity to be able to protect it. It doesn't add value, that it's something that you are protecting. IoT, system integration, simulation, of course. The bit that puts all these together is artificial intelligence. Thank you for watching my short presentation on general purpose technologies. Thank you and au revoir.